simulation of the coupling between the electromagnetic and the mechanical field. I will start with some motivation. It's an injection valve used in automotive industry, a long-term project with industrial partners already some time ago. We will go in some details towards the electromagnetic field, which means the modeling starting from Maxwell's equation, and then also looking at some special properties, deriving the final partial differential equation, which will be a partial differential equation for the magnetic vector potential. Since it is a nonlinear partial differential equation, nonlinearity is within the permeability or reluctivity, so the relation between B, the magnetic flux density, and H, the magnetic field intensity, I will provide you a general framework via Fréchet derivatives, how you can derive a Newton formulation for a nonlinear partial differential equation, and clearly we will use the partial differential equation of the magnetic vector potential describing the eddy current case of electromagnetics. Yeah, and then we will go into detail concerning the coupling terms. As already told, we have coupling terms. The one is clearly the electromagnetic force. So we have Lorentz forces, so current carrying conductors in the magnetic field, but also pole forces, especially, for example, we have in the injection valve when there is a change in the magnetic permeability. And we have a second coupling, which is a very nasty thing, and that are the eddy currents being induced due to moving electric conductive bodies, and these bodies even get into contact. So what to do with the finite elements you have in the air gap before the air gap closes. We will have here some ideas or provide you some ideas how you can solve it. We will not go up to problems where you really have contact, but for a lot of other problems where the working distance is restricted to have no contact, we will show you some special method how you can cope this. Yeah, and at the end we will discuss how the overall computational scheme looks like when you solve magnetomechanical systems. So here you have a view of electromagnetic valve is used in injection system for motors in in cars. So in this sense, this is the main part where where the fuel comes in and then is injected into the cylinder. What we have here is a very simple device, and it is already an old device, but the main project we were working on is how we could reduce the delay time. And the main enemy we have in electromagnetics are eddy currents. And if the eddy currents also generate a magnetic field, which is opposite to the primary magnetic field, and that more or less results in a delay. So the dynamics is not as fast, or was not as fast as we wanted. And I will show you a modern injection cycle, and then you will understand why we had to do this. In parallel, there were also projects. We were also involved with piezoelectric stack actuators as the main actuator in injection system, and clearly a piezoelectric actuator is as fast as you want, because the only delay is the inertia forces you have, because it couples, the mechanical field couples with the electrostatic field. But these devices are quite expensive, and since the manufacturers of magnetic valves have improved heavily the dynamics, now in most of the cars you will still have these electromagnetic valves. But as you can see, we have very few components. We have a housing made of iron. We need the coil, and we have the armature which can move. These are the pole shoe. We will also have a more detailed view. Yeah, and that's it. So it's standard material you can use, and also the fabrication is not so expensive. So here we have a detailed view, and especially when we zoom in here, you see this is the air gap. The standard air gap is about 40 to 60 micrometers, and you should be able to close or open it within 80 to 100 microseconds. So the stroke is not large, but anyway, to get such a dynamics to close or open it within 80 microseconds, it's not easy because we have here iron parts, they have electroconductivity, we will have eddy currents, and so we need here a special design. This is the armature here, which moves, and that's going down here, and which then opens with a needle or closes with a needle the fuel inlet. Yeah, we have the pole shoe and the coil and the housing, and that's all more or less what you need. However, to really be able to do this within a modern injection cycle, you need a very high dynamics of such an actuator, because a standard injection cycle now consists of, as you can see, 5 injection. You have 2 pre-injections. With the pre-injection, you put very few fuel within the cylinder, and there you warm up. Yeah, due to the warming up, you can reduce the generated noise. You have the main injection, and you have 2 post injection, as you can see. And with the post injection, you can reduce at the end the pollution. So what is involved here? The electromagnetic field. It is a subset of Maxwell's equation. As I have told you, it's the eddy current case. We have to consider the nonlinearity, so the nonlinear pH curve. We have to consider motional electromagnetic force, so the induced eddy current due to the movement, very important, because these eddy currents, they really also generate a magnetic field acting against the primary magnetic field and makes a delay. And we have to compute very precisely the electromagnetic force, which will couple to the mechanical partial differential equation. From the mechanical point of view, well, it is linear elasticity. However, when you also want to compute it up to contact, then it's a nonlinear problem. Contact is a nonlinear problem. And due to the contact, you get vibrations, and the vibration lead to the excitation of the sound. So when you are also interested in the generated sound, then you also have to solve the linear wave equation. In this case, this is then really a linear partial differential equation. The excitation is due to the mechanical vibrations. As perhaps you know, the coupling between mechanics and acoustics is also a coupling from acoustics to mechanics by the pressure forces of the acoustic field, but that you can neglect in this case. They are so small that they can be fully neglected. So it's not necessary to take this into account, which means the acoustic field, the acoustic generated sound, the noise, you can also compute in a post-processing when you store the mechanical vibration of all the individual parts, and then in a post-processing compute the acoustic field. Okay, so let's have an introduction and some details concerning Maxwell's equation, and then the subset we will go on, which will be the eddy current case, or quasi-static case as it is called. As you know, the full Maxwell's equation we can subdivide in a low frequency part and a high frequency part. For the high frequency part, we model more or less waves, but neglect especially a lot of constitutive equation, because we have let's say, at least just materials involved, which we can model by linear constitutive equations. For the low frequency range, that is exactly the electromechanical range also, it could be even reduced to the electrostatic case, which would be then the case of electrostatic actuators, mainly used in MEMS devices, so micro electromechanical systems devices, or into the pure magnetic case, which could be the static one, if you have no time dependency, or the magnetodynamics one. We will clearly concentrate on the magnetodynamics one, and the subset is also called the quasi-static case or eddy current case. In Maxwell's equation, we have involved quite a lot of physical quantities. They are just listed here. As you know, the primary quantities would be the magnetic flux density, sometimes just called the magnetic field, and the electric field. That would be when we are within vacuum. If we have polarizable, magnetizable materials, we then also have to introduce the electric flux density, or sometimes called the electric induction, and also the magnetic field intensity, because we have also a magnetization which is in the units of the magnetic field intensity, or you can also describe it by a magnetic polarization, which is the unit of the magnetic flux density, so in Tesla. Yeah, and if you have electric polarizable material, as it is the case in piezoelectric materials, then we have also a electric polarization. Clearly, then we need additional material parameters and then equations to be able to solve the full set of Maxwell's equation. And the main material parameters here just written as scalars. So we assume to have isotropic material behavior, the magnetic permeability, or its inverse, the magnetic relativity, electric permittivity, and electric conductivity. So if we are looking now to Maxwell's equation in vacuum, then these are the equations, as I have told you, actually, when we know the current density J, we have the two unknowns, which is B and E, the electric field and the magnetic field. And in addition to describe all physical effects, we also need the Lorentz force term on a charge due to the electric field or the magnetic field when you have moving charges. What is important when we are looking here is that you see we have here these equations with the so-called Nabla operator. That's why I want to turn over and just make a small summary of all these operators. I guess you all know them, but perhaps it makes sense to also look at these operators and the main integral theorems we will then use in this sense. So for this sense, I will just use one note to write it to you. So as you have seen, there is always this so-called, okay, it seems that my pen is not loaded. I hope it's okay when I just once put it in. Okay. So this Nabla operator was still the wrong color. So let's start. So as you know, the Nabla operator is a vector operator where we have the partial derivative with respect to x, with respect to y, and with respect to z. And t is the transposed. And we call this the Nabla operator. And the nabla operator can operate on a scalar quantity phi, which we call the gradient of phi. And as you see, with this nabla operator, it is just the partial derivative of the scalar function with respect to x to get the x component, the partial derivative with respect to y to get the y component, and the partial derivative with respect to z to get the z component. They put it transposed. This nabla operator can also operate by the scalar product on a vector v, and this gives a scalar. So you see, you reduce the dimension by 1. From a vector you come up to a scalar, and it's the partial derivative with respect of the x component of y with respect to x plus the y component with respect to y plus the z component with respect to z. And it's also important, so we call this also, we write it as the divergence of v. And the divergence of a vector field gives you the sources and the sinks of the vector field, which also means if the divergence is 0, as it is the case for the magnetic field, then it is divergence free, and it means you have no magnetic charges and you will have a pure solenoidal field. On the other hand, we can also operate via the vector product on such vector v, which I think is most easily written in the sense that you write it as a determinant of the unit vector x, y, z. The second line is the nabla operator, so the partial derivative with respect to x, y, and z. The last line are the components of the vector. And when you develop it now along the first line here, then we get the x component by this computation of this subdeterminant. So I write here it as follows. We see it is dvz dy minus dvy dz. The y component is then the sub, when we cancel this column and this row here, and the subdeterminant is the partial derivative of the z component of the vector with respect to x, and the x component with respect to z. And we should not forget that we have to multiply with minus 1, so it is dyx dz minus dy z dx. And the last one is then the determinant of this submatrix here. So you see this dy, the y component with respect to x minus the x component with respect to y. Yeah, as you see, what we get out is again a vector, and if the curl of a vector is different from 0, then we get somehow the vorticity of this vector. Yeah, and that is also a very important thing, and we will see that the generation of such a vector field, for example, is then another vector field as we have, for example, in the relation between the electric field and the magnetic field. A very important theorem is Helmholtz, which we will heavily use. So the so-called Helmholtz decomposition, and we will even use strongly within the electromagnetic field, because it tells us that each vector field can be decomposed into the curl of a vector plus the gradient of a scalar function. And we call psi a vector potential, and we call phi a scalar potential. And what is important is that by the curl of psi, we describe a solenoidal field, and by the gradient a irrotational field. Yeah, and since we know that the magnetic field is divergence free, the magnetic field P, and that we will also discuss later on, is described by the curl of the magnetic vector potential. Yeah? And why it is? Because we have that the divergence of P is 0, and when we put it in, we have the divergence of the curl of A. Yeah? And that is always 0. So you see how important it is in this sense to have this Helmholtz decomposition. And we have a magnetic field, and that was an addition done by Maxwell, that the divergence is really 0. We have no sources for the magnetic field, so no charges for the magnetic field. On the other hand, we will see the electric field. The electrostatic field is a pure irrotational field, but the general electric field has a irrotational part and a solenoidal part. Yeah, and that is also important. For example, I just use now the electric field is very often described by the gradient of a scalar potential. We always put the minus because we know the gradient is always showing towards the largest increase of the scalar potential, but we know that the field lines go from the higher potential to the lower potential. That's why we put a minus. So I write here electron one problem. Okay, that was a little bit too fast. So, for example, electrostatic field. Yeah, and that is because we know in the electrostatic field we have the property that the curl of E is 0. And this is automatically fulfilled when we introduce the scalar potential, because the curl of a gradient is always 0. So you see, this is the very important part in this sense. This Helmholtz decomposition and all these properties we have between the curl and the divergence and the gradient concerning vector and scalar potentials. What will be also very important for us and we will use are the integral theorems. And for this, we have that when you integrate over a volume, the divergence of a vector, then you can rewrite it as the closed surface integral of this volume by the vector itself dot product with the surface. And we know that we can also write as the normal vector. The normal vector is characterizing the direction of a surface and always points out of the volume. So we can rewrite it also with the normal vector. And as you know, this is Gauss. And the other very important and frequently used theorem is when we integrate over a cross section the curl of a vector. Let's use u d gamma dot product d gamma prime. That is the same as taking the closed line integral. Therefore, I'll use partial gamma u in the S. And as you know, that is Stokes. And what we also will need are the integral theorem of Gauss. So I write it here, the integral of green, sorry, theorem of green, because especially if we have a standard equation, then we can rewrite it as follows. If we have minus the volume integral of a function v, scalar function, divergence of any material parameter depending on space, that was too fast, gradient of phi, the omega prime, then this is equal to, and that is very important for us because I think you already all know that we don't solve the partial differential equation, we solve a weak form. In this case, v is the test function and phi, for example, is our physical unknown, the scalar electric potential. Then we have here epsilon of x, gradient of v in gradient of phi d omega minus the closed surface integral of v epsilon of x and then the gradient of phi in n d gamma, which we also can write here as d phi dn, so the normal derivative. For me, it is just important that you see in this sense that this would be not as easy to be evaluated because the Nabla operator is a operator taking the partial derivatives with respect to the space, and we have here a material parameter which could jump, so that is really a problem. On the other hand, when we use this integral theorem, you see that there is no Nabla operator anymore operating on this material parameter. That is a really nice thing. And you can see you can transform this exactly without any approximation to this new volume integral, where now the unknown has just a first order spatial derivative. Clearly also the test function v has a spatial derivative, and this additional surface term. And especially for electromagnetics, we need also the vector form of the green integral theorem, and that is as follows. So you have here the volume integral of a test function, which is a vector, and we have the curl. Now I use here already the permeability being a function of x, the curl of u, which would be in our case at the end then the magnetic vector potential, and that you can rewrite as a volume integral where we have here the permeability without any derivative, and we have the curl of v dot product with the curl of the unknown u d omega. So we have reduced the order of the spatial derivative on our physical quantity u, and in addition we also have a surface integral d omega of v x curl of u dot product with the normal vector d gamma. Okay, and that will be the vector form of the integral theorem of green, and that we will also use. So I just surround this a little bit because that's the important part for us for electromagnetics. When we turn over the strong form of the partial differential equation to the weak form. Okay. Yeah, what coming now back we have also these nice interpretations that, as you can see here, we have the first Maxwell's equation with the correction of Maxwell. Actually, it is Ampere, but the correction of Maxwell was done by this term here, so that we can also describe wave propagation. And we will also call this the so-called displacement current density. So you see here the curl of B is equal to these two terms. Yeah? So the vorticity of B is described by these two terms. On the other hand, the vorticity of the electric field is described by the time derivative of B. So you see this relation here, and if you would cancel out this term here, you would see a time-changing electric field generates a magnetic field, a time-changing magnetic field generates an electric field. Then we have the Gauss law, so we see that the divergence of the electric field is different from zero if we have electric charges. So we have here sources of this field, and which has been added by Maxwell, the divergence of B is always zero. So it is a pure solenoidal field. Here you see you have an equation describing an irrotational field. This is an equation then where you describe a solenoidal field. And we also need the Lorentz force as already introduced. Which is included here is the continuity equation, which is just to perform the divergence on equation 1. Then the divergence of the curl is 0. And when we use also this relation here, then we get the continuity equation for the current and charges. When we have polarizable and magnetizable materials, then we introduce additional physical quantities, and that is D and H. And so in this sense, then we have this set of equations a little bit different as the equations before. We have the current density in electric conductive body, so having free charges, so or possibility that the charges can move freely, and we have these free charges in the Gauss law. In order to get a set which you can solve, we need additional constitutive equations, and these are here, as you can see. The magnetic flux density can be described by H plus the magnetization, or if you combine the permeability of vacuum and the magnetization by the magnetic polarization vector, and very similar to the electric field where we also have an electric polarization vector. So let's have some details about the different laws and the extension by Maxwell. We all know that if we have a conductor carrying a current I, that there will be forces acting, for example, as here on magnetic needles. And one can show that actually these forces are due to a physical field, which we call the magnetic field. And the field lines are looking like this, as shown here. And one can derive, and that has been done by Ampere, that we have this relation if you take a closed contour integral at any contour, but it encloses here the conductor of this magnetic field, that you always get out the total current in the magnetic field. And as you know, this now is easily to be described because you can use Stokes' integral theorem. Then we have the curl of B being integrated over a surface, and the current can be described by the current density, also the integration of the current density over this surface. And since it is the same surface, then we get out this relation with the current density and the magnetic field B. When we apply the divergence, we know the divergence of a curl is always 0. So we have that the divergence of the current density is 0. However, we know that the continuity equation is this equation here. So it's the divergence of the current density minus the change of the currents with respect to time, which means this law of Ampere is just fulfilled in magnetostatics but not in magnetodynamics, as we can show here. If you have here such a setup where we have a capacitor, then it is not a closed electric circuit in this sense, because we have here the two electrodes, and in between you can find such a balloon shaped surface as shown here, and this doesn't unclose any current, although we know a current is flowing. So with this equation we should get out that there is no current within our structure. However, we can resolve it, and that has been done by Maxwell, exactly due to this relation we have, that we substitute now the relation between the charge density and the electric field, so which is given by the permittivity of vacuum and the divergence of E. And if you exchange it, then we can rewrite it in this form. And so we see that also this part here has the unit of a charge density, which we call the displacement current density. And so you can extend your partial differential equation by this additional term what we have here. And what is interesting now is that due to this relation, we see that the time varying electric field induces a magnetic field. And from Faraday, we already know that the time varying magnetic field induces an electric field. So you have this very interesting physical mechanism between the magnetic and the electric field. Now we can resolve very simply our problem with the electric circuit, because the electric field can be described by the surface charge over the permittivity of vacuum, which is equal to the total charge divided by the surface of the electrode. And so in this sense, this epsilon 0 partial time derivative of E gives you a current over the cross section. And that resolves our problem. Now you can make any Ampere's loop once the electric field is 0, and we have the current in the conductor, and within the capacitor we have no current, conducting current, but we have this term here, the so-called displacement current. And so in integral form we have this part here where we have this additional extension resolving everything. What is for us important is Faraday's law, so how a magnetic field generates an electric field. And these are the three experiments, and the classical experiment is experiment 1. You have a moving loop here in a magnetic field, and you can compute the electromotive force voltage by the total change of the magnetic flux, which is just a cross-sectional integral over the magnetic flux density. However, if you look at experiment 2, then you cannot describe this in this sense, because we have here the loop being stationary, and just this part here where you have the magnetic field is changing. So from the point of view of special relativity, that's not a problem, which is moving. But from classical electrodynamics, we need now this addition, that what we have already discussed, that we need this electric field. So because a variable magnetic field change generates an electric field. And that is called induction. And so we also get it by the formulas, this relation. Very interesting is that you still can describe it by the changing magnetic flux. Okay, so this is the relation now that you integrate closed line integral the electric field, which is generated in this sense by the change of the magnetic field, and you can put the total change within the integral where we have a partial derivative. Yeah, and in this sense we then can apply the integral theorem of Stokes on this term here, and since we integrate both terms on the left and right hand side over the same cross section, we see we can neglect it and we get exactly the second equation of Maxwell, that the curl of E is equal to the time derivative of the magnetic flux or magnetic field. Also in experiment 3, where we have a time varying electric current, it has to be described by the induced electric field. If we also have polarizable material, then we know that we have bounded charges being described by the polarization. It's exactly the divergence of the polarization, and the magnetic polarizable material, we have a polarization current density described by the curl of the magnetization. So this is also very interesting, the description, in this sense that once we have really the curl on the magnetization and here the divergence on the polarization. In the dynamic case, this is not enough. In the dynamic case, especially for the polarizable material, we have to consider such a setup, that there is also the situation of the change of the polarization. So if we look at the simple tube where we have minus sigma b, so the bounded surface charges here and bounded surface charges here, there can be a change of these surface charges, which we can describe by a current, which is the change of these bounded surface charges, which are equivalent to the polarization, electric polarization. So in this case, we also have to introduce a further current density, which is described by the change of the electric polarization. This also clearly fulfills, as shown here, the continuity equation for this bounded current density, that this is equal to the change of the polarization charges. So which means at the end that we have a current density which is due to free electric charges which can move, which is due to the magnetization, and which is due to the polarization, and they are described by the magnetization and the electric polarization, and the charges we can describe by free charges which can move, the bounded charges which are described by the divergence of the electric polarization. Now we can combine this in such a sense that in Gauss' law we not only have these free electric charges, we also have the bounded charges described by the electric polarization. And if we combine this via our extended constitutive law, so we introduce the electric displacement, or flux density also called, then we get a final equation where on the right hand side we just have the free charges, but we include all the polarizable effects into it. And the same is for Ampere's law, where we have now these three charge densities as we had it here. We should not forget this additional term as we have discussed before. And due to the relation, when we introduce H, then we can combine this magnetization with B to get H, and this term and this term we combine, as we have seen here in D. And so we get here extended Ampere's law in differential form, where the curl of H now is equal to the current densities in conductors plus the change of an electric field, in this case in space. What is still important is that we force that the divergence of B is equal to 0 to guarantee that the magnetic field is a pure solenoidal field, because still we have not found any magnetic charges. And mathematically speaking, that we have to force, because if you look at this relation we have, then via the divergence theorem we get that the volume integral of the divergence of B is 0, and then we get also locally the divergence of 0. But looking at Maxwell's equation, we can, for example, take the divergence of the second Maxwell's equation coming from Faraday. Then we know that the divergence of the curl is 0, and we have the divergence of the time derivative of B. So if we exchange space and time derivative, it means that the divergence, the time derivative of the divergence is 0, which would mean that the divergence of B still can't be constant, and it can be different from 0. However, since we have no magnetic charges, we have, in addition to force, the divergence of B has to be 0. And that brings me to the reduced set of Maxwell's equation, which we will use in the eddy current case. So in this sense, we will neglect this displacement current density. So in our first Maxwell's equation, we will just write here this is the current density, and what we mean is clearly the free current density. The second equation is already a little bit different. We have just here one part of the electric field, but that's clear, it's just the solenoidal part, because the irrotational part can be described by the gradient, and the curl of the gradient is always 0. So here in this equation, we already can use that we just put in here for the total electric field, the solenoidal field. We have to force that the divergence of B is 0, and we have the general Ohm's law that the current density is equal to the electric conductivity of the total electric field plus the any moving charges cross product with B and the extended material. With the decomposition, as already told, I want to show you that, as I have told you, according to Helmholtz, we can decompose the total field in the irrotational and the solenoidal part. And the irrotational part is always described by a gradient of a scalar function, which would be the scalar electric potential, which means it's not necessary to take within this equation here, so second Maxwell's equation, the total field. It's more or less enough to just take the solenoidal part, because we will also decompose now the electric current density into a current density which we know, which is the impressed current density, for example, in a current loaded coil, plus here this Ohm's law, where we have here the solenoidal part of the electric field and this term when we have any moving deforming bodies in a magnetic field and which have a conductivity. Otherwise, this term clearly will not show up. Now, since the divergence of the magnetic field is 0, this is automatically fulfilled when we express B by the curl of A. So you see, when we introduce the magnetic vector potential and we go back, then the third equation is automatically fulfilled. So we don't have to consider it anymore. Now let's have a look to the second Maxwell's equation. The third we automatically fulfill by expressing B by the curl of the vector potential. Here we have the following. We already expressed the magnetic field by the curl of A, but we have here the curl of A and we have here the curl of the solenoidal part of the electric field, which will give up the eddy currents in any conductive bodies. And we can exchange the time derivative with the space derivative, which means when we bring then this term to the left-hand side, what we have here is the curl of this solenoidal electric field part plus the time derivative of the magnetic vector potential. And that has to be 0. And this is clearly 0 when we express the solenoidal part of the electric field by minus the time derivative of the magnetic vector potential. Yeah? Because then this term is 0, and if this is 0, the curl is always 0. Well, if the curl is 0, you could express this by the gradient of a scalar potential, but, well, why we want to express it by the gradient of a scalar potential when we just have solenoidal parts? This is a solenoidal field, the vector potential is a solenoidal field. So in this sense, we directly express ES by minus dA dt, which means that also the second Maxwell's equation is fulfilled when we use this relation. So this brings us to the first Maxwell's equation, where we have here this part is the magnetic field density. So we have used here the curl of A, which is the B, and by the material law, mu is the magnetic relativity, which is 1 over the permeability, we get the magnetic field intensity H. And that has to be substituted first by the magnetic field B via the constitutive equation, and then we have introduced that the magnetic field B has been described by the curl of A. So this is then our left-hand side. We have here the impressed current density. Then we had within our decomposition the gamma times the solenoidal part of the electric field, which is described now by this term, since we expressed the solenoidal part of the electric field by the time derivative. And we then have the last part, which is the motional EMF. I just want to go back to this equation, which is here, and where we had this full current density. Okay, so I like quite heavily this form to come to an end, because that shows us any eddy current densities being induced to a time-varying magnetic field. I need a change in time. And the second part, even A can be constant, so we can have a constant magnetic field, but we have any moving parts with the electric conductivity different from 0, which we also call the motional EMF electromotive force term. Okay, I think that it's quite a lot we have discussed today. This is our final equation here, and this equation we will then have a detailed discussion next time how to solve this equation here with the finite element method. Especially we have also included now this term here, which comes up if we have moving deforming bodies within the magnetic field. Okay, so this we will do the next time, and then look for the finite element formulation and what is really modeled by this equation and what perhaps is not modeled, and this we will discuss next time.